Hello, welcome to Data Science with EJD. We're still talking about reinforcement learning. Of course, under the playlist is data science, and under data science, we were moving and we moved to machine learning. Under machine learning, we discovered that there are three types of machine learning, so to speak, or machine learning algorithms can be broadly classified into three major classes of algorithms. First of all, you have supervised learning, which is about machine learning from labeled data. And by labeled data, we mean data that has inputs and outputs, meaning that those inputs are features that determine a target. So the features are the inputs, while the target is the output. So another that we saw algorithms like classification and regression. Then from there we moved on to unsupervised learning, which basically deals with machine learning from unlabeled data. So there you don't instead of having inputs and outputs, you just have inputs because all you're interested in is to group data points together to discover patterns and all of that. All right. So you have just the features or what you can call the input, and then grouping them together. And from under that we saw I think two major types of algorithms. It was that two or three? Yeah, we saw first of all we saw clustering, that we also saw dimensionality reduction. I think yeah, there's one more. Association rule learning. Yeah, we saw all of those three classes types of algorithm under unsupervised learning. And afterwards, we are here now talking about reinforcement learning, which basically deals with an agent in an environment in a particular state with some actions available that will make it transition to other states in the environment. And whatever action it takes, whatever if an action taken results to positive reinforcement, then positive reward rather. So that more of that action is taken, and that is why it is called reinforcement learning. So, but if there are actions that lead to undesirable situations, undesirable outcomes, then less of those actions will be taken. All right. So, and here, in this video, we're looking at cutting-edge reinforcement learning topics and extensions. Now, we've seen some topics, specific ones like dynamic programming, Markov decision processes, and things like that. And of course, in the last video, I think we saw, what was that now? We saw policy gradient methods. All right. So which are opposed, which are not, which are, a different set of methods apart from the value-based methods like Q learning and deep Q networks and all of that. So here we are looking at some of those. I mean, some other topics and extensions in reinforcement learning that we should pay attention to. So cutting-edge reinforcement learning topics and extensions, the overview. This guide covers modern methods that push reinforcement learning beyond basic value-based or policy gradient algorithms. So basically, we have value-based algorithms and policy gradient algorithms. So here we are looking at some advanced algorithms, right? Some modern algorithms. So these address real-world challenges like continuous action spaces, data efficiency, safety, interpretability, and multi-agent coordination. So if you like, you can group reinforcement learning algorithms into value-based algorithms, policy gradient algorithms, and of course these modern algorithms, which you can see as cutting-edge reinforcement learning algorithms. So the first of this would be about continuous action spaces and DDPG. I think we had saw something about DDPG in the last video. So now, what is continuous action space and DDPG? Many real-world problems require controlling actions that are continuous valid, e.g., steering angle, motor torque, chemical injection rates, and things like that, especially when you talk about autonomous vehicles and all that. So, and then DDPG is deep deterministic policy gradient, which is an off-policy actor-critic algorithm designed for settings like that, for real-world problems requiring controlling actions that are continuous valid. And how does it work? You have an actor which learns a deterministic mapping from state to action, and then you have a critique which learns the Q value for state action pairs. And the uses, you can use it in replay buffer, which stop past transitions for sample efficiency. You can use it in target networks for smooth outlining by slowly updating target actor or critic. Then the strengths, it handles high dimensional continuous actions and it's sample efficient due to replay buffer. The limitations, it's prone to overestimating key values and it is sensitive to hyperparameters and exploration noise. Applications, you can use it in robot arm control, continuous locomotion, and industrial process control. So that's one area of reinforcement learning that is cutting edge. So let's have the second, which is the twin delayed DDPG. I think we made mention of this a couple of times, especially when we looked at Markov, Monte Carlo, uh, Monte Carlo processes, Monte Carlo prediction, and of course time difference prediction. So we talked about twin delayed, some twin kind of thing. So here we're talking about the twin delayed DDPG, TD3. So the motivation is to fix instability and overestimation in DDPG, and that's why it is twin delayed, right? And the key innovations, you have twin critics, which use the minimum of two Q value per estimate to mitigate overestimation bias. Then you have delayed policy update. So actor is updated less frequently than critics. Then you have target policy smoothing. You add noise to target actions to prevent the policy from exploiting errors in the critic. And the result is that it's more stable and robust than DDPG for challenging continuous tasks. The applications, you can find it in benchmark tasks like Walker 2D, Half Cheetah, Hopper, Mujoko environments. So, and the third cutting edge algorithm we need to know about is the soft actor critic, SAC. I think we have a Python code to demonstrate this particular one, I believe. So the motivation here is you have deterministic policies talking about DDPG slash TD3 can under-explore and get stuck in suboptimal policies. Because those are the two things we had considered before. So SAC can take care of that because it's stochastic in nature, right? So the key principles, it has a stochastic policy. So it learns a distribution over actions, not a single best action. Then it has maximum entropy. It's maximum entropy reinforcement learning. So it encourages exploration by maximizing expected return plus entropy. Then it's off policy. So it uses a replay buffer for data efficiency. Then the advantages. So it has high sample efficiency and good exploration and robustness to hyperparameters. The typical use is in state of the art. It's a state of the art for continuous control problems like robotics, manipulation, and simulation tasks. Then we have another cutting edge thing to consider here. That is multi-agent reinforcement learning, MARL. What it is, it studies environments with multiple learning agents interacting simultaneously. I'm trying to think of okay, well, maybe we can look at this as talking about human beings now. We can talk about two human beings playing a game, whatever game, snakes and ladders, Scrabbles, whatever, or two human beings playing video games. We can look at that. But when we can also talk about it in terms of robotics, right? Maybe you have two robots that are collaborating to do a task, or two robots in the same environment doing tasks, or two robots playing games, or something like that. So it studies environments with multiple learning agents interacting simultaneously. It is cooperative in nature, so the agents share a goal. Then there can also be competitive tasks, like agents work against each other, like playing a game on two different sides. Then it can also be mixed. You can have both cooperation and competition. So the challenges. So it's non-stationary environment from each agent's perspective. Then coordination and communication is a challenge. Credit assignment, attributing joint success to individual actions. So those are because you have more than one agent in this situation. You have some problems involving it's not as straightforward as when you had just a single agent in other situations. The approach is now you have independent learners. Each agent learns as if others are part of the environment, and that can be unstable. Then you have centralized training, decentralized execution, CTDE. So you use global state or action info during training. Agents act independently at test time. So you train them together, but then they do their own thing when it's time to make their decisions in the environment. So you have popular algorithms like MADD, PG, that's multi-agent DDPG. Then you have QMix, which is value decomposition for cooperative tasks. And you have COMA, which is counterfactual multi-agent. Application, so you have it in swarm robotics, autonomous driving in traffic. So maybe you have of course even if you have one autonomous vehicle, right? There are other vehicles in the environment. So so the autonomous vehicle has to pay attention to those other traffic, all those other cars driving, or even humans crossing the road and things like that. So autonomous driving in traffic, multiplayer agents, smart grid coordination. Okay, so we have another cutting edge stuff, which is the hierarchical reinforcement learning, HRL. So the motivation is that many tasks have natural hierarchies. For instance, to break big goals into manageable sub goals, right? So it's like the idea of object-oriented programming. So you have a class and then you have some subclasses, some definitions, some functions under the class to make it work, right? So the core idea is to use multiple levels of policies. You can have a high level manager which chooses sub goals and options, and you have a low level worker which executes primitive actions to fulfill sub goals. And the benefits of this will be to for better exploration via temporal abstraction. It's easier to transfer learned skills, reuse sub policies, and solves long horizon tasks more efficiently because the work is distributed. Then you have popular frameworks like options framework, which defines options as sub policies. You have feudal networks, manager worker architecture. You have HIRO, hierarchical reinforcement learning with off policy correction. The applications can be found in household robotics like that require navigation and grasping, game playing like planning multiple moves ahead, complex robotic tasks. Also, then another cutting edge thing we need to know as far as reinforcement learning is concerned is inverse reinforcement learning, IRL. So the problem is sometimes defining a reward function is impractical, right? So, but demonstrations from an expert are available. So the solution is you have inverse reinforcement learning, which infers the reward function that would make the expert behavior appear optimal. So you have the variants like max and IRL, maximum entropy formulation for robust reward estimation. You have GAIL, which is GAIL, generative adversarial imitation learning, which combines GANs with imitation learning. All right. So we have applications in autonomous driving, learn from human drivers. So, I mean, an agent can learn from a human driver or something like that. Then you have robotics, replicate skilled human tasks. And then, like cooking, right? Medical decision making, extract implicit rules from expert actions. So, also we have offline reinforcement learning, that's batch reinforcement learning. What it is, it's so you learn here, it's learn good policies purely from fixed data sets of past interactions, no new environment sampling. So you have available data, and that is basically the basis of the learning, right? So it's not like you're feeding data real time and the system is learning from that. No, so it learns from the available policy. And I believe one of the reasons why it will be batch reinforcement learning is that so you need a new set to update the system. You need a new set of data to come and train on that, and it's not real time. So why it's hard is that new policies may choose actions outside the data distribution, which is you can have unreliable Q values, which can lead to catastrophic exploitation. So if you remember, at some point we're looking at the balance between exploitation and exploration. Exploration is like trying to find new ways of doing things, but exploitation is taking decisions based on the things you have learned already. So there should be a balance between the two, because if you only work on if you only exploit, that is using already known knowledge, you may miss some new things. So once in a while, you also want to go and explore again. So in case you might find something new that works better than what you have been used to already. So the key techniques include conservative Q learning, SQL. I mean conservative Q learning, which is CQL rather. Which penalizes Q values for out of distribution actions. So anything that is out of distribution, any action out of distribution is penalized. Then you have batch constrained Q learning, BCQ, which restricts policy to stay close to observed behavior. Then you have behavior regularization, which encourages learned policy to mimic the data set's policy. Then the applications, you can have it applied in healthcare, policy improvement from logged clinical data, robotics, learning without expensive real-world trials, recommendation systems, improve policies from user logs, right? So, so you can then have another one. You have safe and robust reinforcement learning. The motivation is that many reinforcement learning applications have high stakes. Safety constraints must be obeyed, e.g., collision avoidance. Like for an autonomous vehicle, you want to avoid colliding with other vehicles or hitting a pedestrian and things like that, right? So the challenges include standard reinforcement that standard reinforcement learning can explore unsafe actions that cause system failures. Learned policies may overfit to ideal models and fail under disturbances. So the approach is now you have constrained MDPs. I believe that's Markov decision processes. So you need to add constraints. You keep probability of failure below a threshold, and then you have robust reinforcement learning, train for worst case dynamics with an uncertainty set, within an uncertainty set rather, then shielding, use rule-based or model-based checks to override unsafe actions in real time. The applications now, you have autonomous vehicles, industrial automation, medical treatment planning. So as a practical example, we have SAC for continuous control. So SAC again, don't forget, is soft actor critic, which is non stochastic and make and more realistic than deterministic methods like we learned previously. So here's how to implement soft actor critic on a continuous control benchmark like the pendulum V1. So of course you import gymnasium as gym, and from stable baselines 3 you import SAC. Then you create the environment using the pendulum V1 data. Then you create the SAC agent, so the model SAC ML policy environment variables 1 model.length. Total time steps is 100,000, 100,000 so to speak. Then you test the agent. You have OBS info environment reset, which is fixed. So for the process, right, in range 1,000. So you have the action and the states. So model predict, OBS deterministic is true. OBS should what terminated truncated info and all that. So if terminated or truncated, OBS is reset, environment reset, and then you close that. So if you run that, because it takes a lot of time. I have run it already, so we can just look at the answer directly with the results of the code. So it's pretty lengthy because we're talking about 1,000 processes like that. So of course, it tells us it's using CPU device, wrapping the environment with a monitor wrapper, and wrapping the environment in a dummy vector environment, right? So we have the first step, right? I think what we should be looking at will be these two losses, entropy coefficient and entropy coefficient loss. So here, of course, you can also look at the time steps. So you have 800 here for. Oh, okay. Oh yeah, that's the beginning for sure. So look at those values now. N up to 699, then it moves to 1499, and then you look at the values improving. The actual loss is 18.1 initially, then it moves to 40.9. The critical loss is 0.234, and then that moves to 0.202. Then the other loss, the entropy coefficient is 0.814. Now it becomes 0.65 and all the other values. So it keeps going like that. So if you look at the steps now, 699, 1499, 2299, 3099, 3899. So it looks like it's just increasing by 600, right? Then you have 4699. Yeah. Yeah. Oh, not exactly 600 though. So you have all these values increasing like that, and it just keeps going and going and going. So this took a long time, like maybe like 10 minutes to run. So that's why I had to just run it before so I can just go ahead and show you. So you have all this going on like this. So it just keeps going, 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 you know. So each thing in a box like that comes out after some time, right? So it just keeps going like that, and then we have the result. So up to 99,899 updates like that. And then we have actor loss finally at 16.6, critical loss is 0.676, entropy coefficient is 0.00144. So it has now reduced to that step. So total time steps is 100,000, just like we saw 100 over underscore 000, right? That's 100,000. And that's what we have. So why SAC works well here, pendulum has a continuous torque control signal. Then SAC balances torque application while maximizing exploration. Then it converges quickly and handles the unstable upright equilibrium robustly, right? So the summary table, we have DDPG. The target problem is continuous actions. The key tricks, deterministic actor plus critic and target nets. The example use robot arm. Then TD3 DDPG improvement. So it improves on DDPG. So the key tricks are twin critics for delayed actor and noise. The example is Walker 2D, SAC stochastic continuous policy. So, and the key trick is entropy regularization. It can be used in Hopper and Pendulum. Then you have the multi-agent reinforcement learning, multi-agent systems, and then key tricks CTDE and value factorization. So, example traffic simulation. So, you have hierarchical reinforcement learning, complex and hierarchical tasks. The key tricks, yeah, options are manager, worker. Then example uses household robot. Then you have inverse reinforcement learning, target problem, learn reward from demos. Then you have maximum entropy, IRL, and JIL. So example uses in autonomous driving. Then for offline reinforcement learning, the target problem when there's no new sampling. So you just have all the data at once that you can work with. So you can use CQ, BCQ, and behavior constraints. The example use you have that in healthcare, like logged clinical data. Then you have safe and robust reinforcement learning. So target problem, if there are safety constraints, then key tricks, you have constrained markup decision processes, and then you have robust learning too. So the example uses in autonomous drones. So the next steps we can have beyond this is we can do some hands-on, like try implementing DDPG, TD3, and SAC from scratch in PyTorch. Here we've just used it in a reinforcement learning environment, using gymnasium and stable baselines, basically. So we can try it in PyTorch. Advanced, you can explore multi-agent frameworks like Zoo plus DPG and research, look into safe RL benchmarks like Safety Gym, and you can deploy, you can test on real robots or simulators like Mojoko. So, I mean, if you're in that environment where you're working on robots, this might be things you want to try out for sure. So, with this, we come to the end of this very interesting video. If you have not subscribed already, please go ahead and subscribe. Be sure to hit the notification bell also so you can always get alerted each time a new video is released. All right. And then you can become a member of my channel. Just click on join and you can see different levels of membership you can be part of. And with each one you have a special package, a special perk, a perk for you for being a member at whatever level you choose to be a member, right? That don't forget all my code sheets, my data sets are all available on Google Drive. Just look at the link in the description, either on Facebook or YouTube, and then you can download all the data sets, all the code sheets, and everything, so that I prefer that you learn hands-on. So download everything, set up your system. So as I go step by step, you also look at your device. If there's a code to run it. If you see a number, change it and see what difference it makes. So that way you can learn like that. All right. So be sure to like and share this video also so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.